The following KQED production was produced in high definition.
California may be known for sun-drenched beaches, but any local will tell you, if you're taking a walk along the coast in San Mateo County, you better bring a sweater. When the fog rolls in here, global warming might be the farthest thing from your mind.
Don't let microclimates or whatever the weather's doing on a given day fool you. The fact is that both the ocean and the California landmass are both warming up as a whole, and it's happening faster than scientists expected. There are signs of climate change all over California, and later we'll come right back here to see some of them. But maybe the best place to start is about 200 miles that way and a few thousand feet that way.
High in the Sierra Nevada mountains, California's vital water supply falls in the form of snowflakes. I've joined Frank Gehrke from the State Department of Water Resources here at one of the sites south of Lake Tahoe, where he monitors California's winter snowpack.
We're going to start from here. We'll measure up 50 feet in the direction of that orange sign.
Okay.
Take our first sample, repeat the process.
These studies are crucial to California's farms and cities. 40% of California's surface water originates up here in what Gehrke calls the frozen reservoir. For more than a century, surveyors have been taking core samples and measuring the water content of the snowpack using a hollow pole and a scale.
79 inches.
79 inches.
It's not just how much snow is on the ground, it's how much water is in the snow. The snowpack can run from 50% water density to nearly zero. Since wet snow is heavier, the scale and conversion charts calculate the water content.
The first snow surveys were made basically just over the ridge from where we are now, over on Mount Rose. First one was made in 1906, and if you're looking at any kind of a climate change scenario, that's the key. As far back as you can with a consistent methodology on data collection is absolutely critical.
The combined snowpack measurements from the past 3 years show a trend significantly below historic average. Using decades of data, scientists have determined more rain and less snow is falling at higher elevations. And rather than melting gradually, the snow we get is running off earlier and faster. If this pattern continues, hydrologists fear snow will melt too early for reservoirs to catch it all.
It does seem that snowmelt is occurring earlier. There are records in Yosemite comparing the date of snowmelt now versus 20 years ago, and it's about 2 weeks earlier. 2 weeks doesn't sound like a big deal, but California doesn't get rain in the summertime.
According to NASA, 1997 through 2008 were the 10 hottest years since modern records began 120 years ago. Disappearing snowpack will affect more than just our water supply. California's ecosystems will need to adapt or die.
We should expect that lower elevation trees will be moving up higher, and some of the trees that we associate with higher elevations might be dying off. So we should expect to see major ecosystem shifts that occur.
In Sequoia National Park, hydrologists from UC Merced are scrambling to better understand the inner workings of the Sierra snowpack.
What we need to do is develop some new technology, spot measurements, that give us a better idea of how much snow has fallen, and then we'll know what's going to be there in the spring when it melts.
Conklin's team has installed networks of ground-based sensors in key Sierra locations, a kind of woods wide web.
Let's see if I've got any data coming in.
The data they're collecting will form the first ever map of indicators like soil moisture and temperature, solar radiation and snow depth, even stream flow underneath the snow.
We don't really understand the cycles and the timing and the distribution and amount of water that we're going to get from snowpack in the mountains. The cycling of water through the soil, within the streams, and when we can expect runoff to occur. Those are critical tools that water managers will need and can use in the future.
In order to capture the early runoff, California may be faced with spending tens of billions of dollars to build new or expanded reservoirs.
I think water managers are just beginning to wrestle with the problems of climate change. Figuring out how to capture the water that may run off earlier because it's falling as rain now instead of snow is going to be a new challenge.
Part of the answer may come from other sources of water, such as desalination or wastewater recycling. And Californians across the state will need to conserve.
If we applied technology that we already have to use water more efficiently, then in fact California could be growing, it could have a healthy agricultural sector, it could have a healthy urban sector, and actually use substantially less water than we use today.
The signs of change are all around us. The natural harbingers of spring are arriving earlier. Plants are blooming. Birds are nesting sooner. And as spring turns to summer, the changes may become even more dramatic. June 2008. After an especially dry spring, lightning triggers more than 1,000 wildfires in a single weekend, mostly in Northern California, and more may be on the way. A recent NASA study found that as the Earth warms, the number of lightning strikes in the West will increase. Couple that with a U.S. Geological Survey study confirming trees across the West are dying at twice the historic rate due to rising temperatures and drought, and the future looks highly combustible.
What you see before you here is a very hot, damaging fire that occurred in the middle of the month of May, about 2.5 or 3 months earlier than it would in any given typical year, fire year, which is a great demonstration of how fire regime, fire severity is expanding in California.
Crawford Tuttle, Chief Deputy Director at CAL FIRE, the state's firefighting agency, walked me through one of last year's burn zones. Dry conditions and dying trees make areas like this one a tinderbox.
What you see here is a fire condition that burned very hot. You can look at how the vegetation burned all the way up into the canopy here. And this is an example of a catastrophic fire where there won't be anything left from this fire. You will end up with bare ground.
This is, to some extent, the future.
Most certainly is, given the trends that we're seeing now.
Healthy forests are one of our most effective filters for keeping carbon dioxide out of the atmosphere. But when they burn, that carbon is released. Calculated but aggressive reforestation after major wildfires may help restore some balance. But the climate challenge reaches well beyond the high country. Where land and sea meet, you can cross worlds in just a few strides. The intertidal zone is one of the most dynamic ecosystems on the planet.
The organisms that live here need to deal with the changes that are happening on land as well as the changes that are happening in the ocean. And we've already seen actually a lot of things changing out here. We've seen species moving further north. We've seen some localized extinctions, so species that used to live in a place are no longer there. And we're seeing a lot of sort of interactions of different species that are changing.
Scientists have been studying tide pools for more than 100 years, and what they've been seeing lately has been well outside the range of natural variability. These startling changes have drawn the attention of marine biologists like Eric Sanford.
Well, these tide pool communities have been used for a long time as a model system to help us understand about the natural world. For example, you might be interested in how fish or crabs are doing out in the open ocean. Those organisms are hard to find in the open ocean. They might be fast moving. But these tide pool communities are great because it's really easy to study these organisms. So really we're using these species as model organisms to help understand what happens when temperatures warm up.
And it's easy to see here how the climate can tip the delicate balance within an ecosystem.
One thing we want to remember is that communities like this one have lots of species that live in the same place and they interact with each other.
So what we have here is what we used to call starfish when I was a kid. And
That's right.
I guess word got out that it's not a fish.
Right, so this is its common name is more correctly the ochre sea star.
Okay.
Its favorite food is the mussel. This is the California mussel here. And one of the important things about this mussel is that it's a habitat-forming species. We've been interested in how changes in temperature might affect the feeding rate of this important predator, this ochre sea star. And so,
what are you seeing?
well, changes of a few degrees are enough to increase their feeding rates really dramatically. And so you could imagine in the future, if temperatures in the ocean continue to increase, that the appetite of these sea stars might also increase, and therefore they'd be eating a lot more mussels and decreasing the size of these mussel beds that are habitat for a whole lot of species.
The changes also mean that the original residents may need to either move out or move over for some new neighbors.
So let's see, oh, this is interesting over here. This is a sea anemone.
Oh, yeah.
See it under the rock here?
Yeah, what are you pointing to exactly?
Well, so this here is actually called the sunburst sea anemone.
Okay.
And you can recognize it by the lines that are on its central disc. It's a more southern species. It's found all the way down into Baja, Mexico. And in recent years, it's been increasing in abundance here in Northern California. And it's also being found further up the coast than it used to be. So this appears to be a southern species that potentially in response to these warmer ocean temperatures has been slowly marching its way up the coast. These tide pool communities are telling us a lot about how species might be responding to climate change.
In addition to ocean temperatures rising, the sea level is also creeping up. That's not just theory, it's a real and growing problem.
Sea levels are rising basically for two reasons. The first one is the one we all kind of realize, is that ice sheets are melting and more water is being added to the ocean. But the other reason why sea levels are rising is that the volume of the water is actually expanding. As the water gets warmer, the molecules in the water start to bounce around. So we may have the same number of molecules of water, but they're taking up more space.
As the water itself expands, habitat along the coastline will shrink, changing the dynamics of the intertidal zone.
The organisms aren't necessarily going to be able to just march up the shore. Some things can't survive higher than they are now. So we get something that's called coastal squeeze, which is when sea level rises and the organisms on the shore can't go any further up. So the band that they occupy just gets compressed.
And it isn't just tiny intertidal denizens in danger. Talk of rising sea levels should get the attention of people who live around the San Francisco Bay. If projections are correct, some of the priciest California real estate may find itself underwater.
Over the past century, the waters of San Francisco Bay have risen 7 inches. Over the next century, the waters may rise a meter, 3 feet, 4 feet or more.
Will Travis's agency, which regulates development around the bay, is currently working on a comprehensive regional response to rising sea levels.
What we've done is mapped the Bay Area to see which areas are vulnerable to rising waters. So, downtown San Francisco International Airport, Silicon Valley, Oakland Airport, virtually anywhere that's low-lying flat land around the bay is vulnerable to sea level rise. What we need to be doing is designing the bay for the way it'll be in the future, when it has different water elevations, different salinity, different chemistry, different temperature, and probably different species. We need to be doing proactive, adaptive planning that will put the conditions in place that will react the way we want when those changes come about in the future.
To prepare for and perhaps reduce global climate change, we need a better understanding of what's on the horizon. Sophisticated computer models that project global temperatures into the next century are helping fill in the picture.
We've been trying to look at how man-made emissions are going to alter the Earth's atmosphere and alter the climate that responds to those changes. We're fortunate to have an excellent record of how the climate has changed in the past. It's buried in the ice cores that we've extracted from Greenland and Antarctica.
Core samples reaching thousands of feet into the ice have yielded more than 100,000 years worth of climate data trapped within isotopes and ancient gas bubbles. What they reveal is that over thousands of years, the climate goes through natural warming and cooling periods in a pattern that looks much like a heartbeat. But the warming we're seeing now is off rhythm.
What we're seeing now is occurring much faster. Rather than happening over tens of thousands of years, we're seeing very rapid change occurring on just the timescale of a single century.
Scientists use past climate data to project climate models into the future. This map shows how the Earth's temperature has increased since the beginning of the Industrial Age. The yellows and reds show where the average global temperatures have been rising.
This timeline is showing how the temperature all over the globe has changed since the beginning of the 20th century. And the simulation that we're seeing on the map is sort of a middle-of-the-road pathway. Even in this middle-of-the-road pathway, the whole globe gets hotter. Look at how warm California's gotten, 4 or 5 degrees hotter than our historical climate.
It doesn't take much to make a big difference. Consider that during the last major ice age, the world's average temperature was just a few degrees cooler than it is today. California is now projecting an increase of 3 to 6 degrees warmer by the end of this century.
So people might ask, why should we trust a climate model? After all, it's only a model. We don't just trust the models blindly. We're literally swimming in measurements about how the atmosphere is changing, how plants on land are changing, how the oceans are changing. And we test our models to make sure that they can reproduce those observations from satellites, balloons, measurements on land, measurements from deep inside the ocean. Fortunately, we've been forewarned, and we think we've been forearmed. The fact that people are causing climate change means that we have to change how we produce energy. It's really that simple.
The models can show us some of what likely lies ahead, but the future still holds many questions. What will California look like when our children and grandchildren are raising their families? In Marin County, California's iconic redwood trees may be facing a challenging future. Keely Hamilton, a biologist at the California Academy of Sciences, has studied how California's flora and fauna will respond to the coming habitat shifts.
So I suppose these coast redwoods that we're walking through right now are a great example of a species that's pretty picky about where it grows.
That's exactly right. These redwoods only grow along a very narrow strip of California's coast. And really, where we are now in Muir Woods, right along the coast of the Bay Area, represents exactly the kind of habitat that the redwood required.
Coastal redwoods get much of their annual ration of water from fog. If its frequency and density should decrease, so will the tree's range. The redwoods are hardy old souls who've seen many changes in the climate over the millennia. But as the current models and tree core samples foretell, the predicted rate of change is much different.
It seems like a redwood is one of the few living things you can actually point to and say, well, it's been through so much in terms of climate and survived. Why is what's happening now any different?
It's true. We have individual redwood trees that have survived for so long. They provide a record through coring and measuring actual past climates like ice ages and droughts. They have a record of historical variability, but the speed at which the climate is changing far exceeds what we've been able to measure in the past. And that means for organisms like redwoods, they probably are going to have a hard time keeping up with their shifting climate envelope.
The effects would be subtle at first. Individual redwoods can survive for centuries, but in the projected new climate, they may lose their ability to reproduce, essentially dooming the forests to become tree museums.
Is there any way to know then, with the modeling and everything else, what, let's say, our kids and grandkids are going to how they're going to perceive California? How's it going to be different than it is now?
Well, that's a really difficult question to answer. We can look at what the climate models say about precipitation regimes or temperature changes, but we can't tell you exactly how species are going to respond to that. Can we say exactly which ones are going to survive? What populations are going to wink out? Will dispersal allow these populations to come up in another place? In 50 years, it's not likely we'll see huge differences in the area that we're walking through right now. However, the trend over time is going to be difficult for a lot of species to cope with.
The science is clear. The changes are already underway, with more coming. And the future climate will touch nearly every aspect of our lives.
We're not saying the sky is falling. The climate change over the next 25 to 30 years, we think can be handled with present-day technology. And we're going to have to look at this problem not just as a problem for people, but really as an issue for the whole web of life.
It's going to change how we live, how we get to work, what kind of buildings we're in, how we behave. It is going to be the most profound change that we have experienced probably as a species. But it is also giving us the opportunity to really change things in a positive fashion so that we can live in harmony with nature instead of fighting against it.
The overwhelming majority of the world's climate scientists agree that decisions we make in the next few decades about automobiles, energy, and dozens of other vital issues will set the tone for the next century. In the end, it's up to us whether the transition to a warmer world will be merely inconvenient or catastrophic.
Climate change presents us with more than one conundrum. First, there's understanding how it'll all play out in nature and how it'll affect our own species, among others. And then there's the whole question of what are we going to do about it? These are the things that Quest and Climate Watch will be exploring in the months to come.